and area under the curve is integration, we can use those and the idea of slope and the idea of area to help us solve. So one way that we represent slope was delta y over delta x. You do that in physics. We called that y2 minus y1 over x2 minus 1, or x2 minus x1, and so on. Therefore, if you are solving for area, what you are going to do is the inverse of that. The inverse of division is what? Multiplication. So to find area, one way to do that is take the change in x and multiply it by the change in y, which is what we've kind of been doing when we say, here's the length of the rectangle, that's the change in x. Here's the height of the rectangle, that's the change in y. Okay? Yes, sir?
Is that the dot product? Or?
No, not dot product, multiplying. It was kind of open dot when I wrote it. Okay?
So that's how we do the whole thing.
That's the whole idea between working with both of these. So here's our main formula for the fundamental theorem of calculus. Are you ready? Blow your minds here. No. If we integrate f of x, which we're going to assume is the derivative. Remember we talked about when we were integrating, you could write the derivative as little f and the integral as the big F. This is what this notation is. The integral becomes big F of x on the boundaries a to b. Now, here's the big thing. We've never used the boundaries so far in any other way except to block off this area and say, let's just find the area using geometry. Well, let's just say we don't want to do that, or it doesn't add up to nice little geometric shapes. And we know how to estimate, but estimate isn't perfect, right? So what this does for us in this form is it allows us to say, if I know my new function, f of x, I can take and I can plug in those boundaries. And I can say my area is going to be equal to f of b minus f of a. Big F.
No, like the other ones.
Which one?
Oh, they're all big.
Yeah, those are all big. Or if we use the notation we're more comfortable with, if we're given f prime, we integrate and we say, if I integrate and get back to my f of x, I can take my f of x and integrate from a to b, which is f of b minus f of a. Okay? All right, so what this is going to do for us is it's going to put together everything we've talked about this unit. Remember how we had to solve the differential equation for c in other ways and find c by plugging in values and all of that? When you have boundaries, you don't have to use c. When we have boundaries, we know what numbers to plug in, and we can just find our f of value at that without worrying about the c, and so on. So we're going to take a look at example 1 here. First off, we still need to integrate, okay? So let's just ignore the boundaries momentarily and think about integrating this, okay? First, we need to rewrite our formula because we don't integrate with the root 2 over x, yes? So how do we need to rewrite this in order to help us integrate?
2x to
So I'm going to put under the square root 2x to the negative 1. Now, right now, this is kind of a chain rule, right? I'd rather really not think about that. So is there a way that we can either split this up or rewrite to help ourselves with that root?
1/2.
Yeah, it's a 1/2 power. Do you remember when we did roots with variables and numbers in pre-calc, and I told you you could pull them into 2 separate pieces? No. Okay, so here's what we're going to do. We're going to say, I'm going to just pull that root 2 by itself. And then I'm going to use the 1/2 as an exponent only on the x. So what is that going to make my x? X to the what? Negative 1/2. We all okay with our rewrite on that?
Yeah.
Now, do we know how to integrate something like this? Sure. Okay, do I have to keep the root 2 out front? No, I can pull it all the way to the front, right? I can bring it out there if I want to. And I can integrate my x to the 1/2 by itself. How do we integrate x to the 1/2?
You would just add 1.
Mm-hmm.
By that
Yep, so I do my normal integration. It becomes x to the 1/2, right? What number goes out front?
2, but when you multiply by the root 2, it's just 1.
Right. Now, I'm going to go ahead and leave my root 2 out front of the whole thing here. And there's a good reason for it. So I'll show you that in just a second. We are going to then take this integral, because now notice we lost our integral sign and our dx, but we still have to use those boundaries. So notation wise, you're going to show me that we are going to integrate this from 1 to 9.
Would you put a plus C on there?
No. And so when we're integrating with boundaries, you do not need to put a plus C, because now we know specifically what this formula is, and we can plug in the actual y values. And so with boundaries, there is no need for C. So now here comes this part where we plug in this subtraction. So when you integrate, in order to use the boundaries correctly, you're always going to do f of the top number minus f of the bottom number. It's essentially finding the difference between your final number and the first number, which is the area between them, is what you're doing here. So when I do this, now this is why I left the root 2 out front, because I don't want to use that on every single one of these when I'm plugging in. I want to just use that at the end. So we're going to leave that root 2 out front, and we're going to plug it in. Plugging it in would look like 2 times, now x to the 1/2 is just what? Root x. So I'm going to say root 9 first. Minus 2 root what? 1. Let's just keep working inside the parentheses. We know what the root of 9 is, right? That's just going to be 3, and multiplied by that 2 gives me 6 minus 2. So my official answer, my area under this curve that I've been given, is 4 root 2. And that is an exact answer. It is not an estimate. It's not, doing trapezoid shapes or breaking it into geometric shapes that we hope estimates this. This is the exact area under the curve. And that's what the fundamental theorem of calculus does for us. Okay? All right, so all we're doing at this point, and now that one on that previous homework that we just talked about, that you said the key had some extra stuff on it, makes more sense. We integrate and we plug in the boundaries and subtract, and that's what you saw on there. So that's about what we're looking at here. If we want to integrate cosine from 0 to pi, we'd like to find the area under the curve, okay? We use the integration of that. What is the integration of cosine? Sine on the boundary 0 to pi. Therefore, to find that, we plug in our boundaries. Which one first? Pi. So we do sine at pi minus sine at 0. So sine at pi is what? 0. Sine at 0 is, therefore my answer is 0. Now if you think about the cosine function on the interval 0 to pi, well the cosine function looked like this, right? 0 to pi is here. It has some above and it has some below. Does it make sense that that would be 0? Yes, it does. So visually speaking, it helps you deal with the positives and negatives without even worrying about them. Okay, it just takes it and does it in our formula for us. Now, some of these, you are going to get into some that there is no way to do what we just did. I already kind of alluded to this the other day, but if you are asked to integrate the absolute value of x minus 1 on the interval 0 to 3, do we know anything about integrating absolute value? No. So if you cannot integrate something, we revert back to what we just did on the last homework. Do I know how to graph the absolute value of x minus 1? Yeah, that's an absolute value function that's moved which way? Right one, because it's inside the absolute value, right? So I take my absolute value function, I know it's moved right 1 and has a slope of 1 going this way. So it would look something like this. I would like to integrate this on the interval 0 to 3. So 0 to 1 is this triangle in here. Okay, out to 3 would be something like this. Now, do we know enough about this parent function to figure out these areas? We sure do. Okay. What about this little area right here? 1/2 base times height is going to just be 1/2 times 1 times 1, so 1/2. What about this one? Do I know what the height of this triangle is? It's 2 as well, because I know the absolute value function has a slope of 1. So that's going to be 1/2 times 2 times 2, so just 2. So then what would my integral be from 0 to 3? 2.5, 2.5, 5/2, whatever you want to say it is. So it is possible that in the midst of some of these that we do know how to integrate and find an exact area, you will have some that you don't, okay? And this is where parent functions come back. So things that you might be asked to integrate without actually doing the integration, absolute value, we don't know how to do those. What other equations do we not know how to integrate yet? Think about parent functions. The E one, logs one. Okay, so, but if you know how to sketch a basic graph of it, you could use the equation to at least give a representation of it. Like, let me just throw out, let's just say, I don't know, let's go 0 to 3, e to the x, like just that parent function. What's that look like? The e to the x goes which way? It's an exponential, right? What point do we know it goes through? 0 up 1, right? So it looks something like that, right? And if I wanted to integrate on the interval 0 to 3, now this is not going to be super nice, probably. It would be an estimate. It would be finding this area under here, okay? So you could, on this one, I could have you just do 3 rectangles, like do a right-hand Riemann sum, and you could say, all right, this one is represented by e to the first. This one is represented by e to the second. This one is represented by e to the third. Even though we don't know what those numbers are, you could tell me that area is basically going to be estimated by e to the first plus e to the second plus e to the third. But knowing enough about your parent functions, you could, plug in some of that information and give me an estimate. It might not be an exact, but it's possible that we could do things like that, okay? Now, I do want to give you just another 1 or 2 to practice yourself. I think the back page is blank. Okay? Yep. All right. So flip to the back real quick. I'm just going to give you 1 or 2 questions to practice your integration with this plugging in. I know it's not that hard, and I do want to give you a good chunk of time to look at test corrections today. But just I want to walk away having done at least like 2 more. Okay? So let us do the integral of, let's do -1 to 1 of x squared minus 2 dx. All right, so we integrate those, and then we're going to go on the boundary, -1 to 1, right? So which one are we plugging in first? The 1. So if I plug in 1 to those, what am I going to get? 1 over 3 minus 2. We'll deal with the fractions in a minute. Now, careful on this one because we're minusing. Let's see what we minus here. When I plug in -1, I'm going to get out -1/3 plus 2. But you're subtracting. Okay, so we just need to be a little bit careful with that. Because that's the formula. It's f of b minus f of a. Yeah?
When you get positive there because the -1/3.
Oh, yeah, we're going to distribute here in a second. Yeah.
Like, no, but.
This?
Okay.
-1? Yeah. Okay. So then minus a negative, I'm going to distribute. So I've got 1/3 minus 2 plus 1/3 minus 2. So total of 2/3 minus 4 in terms of thirds. 12 thirds. So I get negative 10 thirds as my final answer on that one. Should we practice one more? Sure? Okay. Let's do the integral from 0 to 3 of 3x squared plus x minus 2 dx. All right, so we just have to simplify this, and we say 27 minus 6 is 21. In terms of halves, that's 42. So I get 51 over 2.
That's right.
Is that right?
Yeah.
Yeah? All right. We are done.